streaming is on and the recording is on, and I would like to use this view. Let me just put this off. All right, so I would like to use this view. Now, let me just check it out before we get started, like how I look, because for online participants, I need to apologize that I'm very close to camera. And the reason for that is that I don't have any other mic system today other than the mic that is located in this camera. So let me put this a little bit up. And that's why I need to be standing close to camera. So next time you're watching this recording, my face will be like this big in your screen. But, you know, that's the only way to go today. And again, the reason is that I borrowed my USB divider to one of the professors in the Department of Mechanical Engineering, and he did not return that to me. So I don't have my USB divider, and that's why I only can use my camera system, not to my mic system. But without further ado, today we have a very exciting day. Now let me tell you why. Let me put this off. So we have a very exciting day because if everything goes as planned, we are able to run the first analysis today. Yes, we're able to do so. And you may wonder, like, really? So because we have just a few ingredients so far, so we haven't learned that much. So how it is possible that we can run first analysis already this part of the course? Now let me explain you something. You know what we learned was that we learned that we can express the constraints such the way, hold on, let me put the writing on. Constraints such the way that they are function of generalized coordinates, possible time too. And if we are dealing with kinematically driven system, then we have equally many equations as number of unknowns. What is that? Well, it means that we have all the information to solve this problem, because basically what we need to solve is this, generalized coordinates. And this will be solving the set of nonlinear algebraic equations. You know how to do that because you learned that from the mathematics course. Today we can apply that to multibody dynamics, and we will solve the response of kinematically driven system. Makes sense? Already this time. So it will be exciting time, and few ingredients prior to that analysis, and we need to learn a little bit more about the constraint equations. Still, there is something that we are not sure, and we need to practice a bit more. We need to learn more about how to compute the number of degrees of freedom. We need to, look at the different types of constraint equations, because so far we look only. How is my writing here? Oh, the end is a bit loose. So we learned that how is a revolute joint, but we need to learn how is a different type of joints, how we can model, say, primitive joints, translational joints, basic stuff. And that's what we're going to do before the kinematic analysis. And then, at the end of the day, we're going to take a look at something called Jacobian matrix, which is related to this kinematic solution. And you already kind of see, so this is how the Aki is going to solve the set of nonlinear equations. So it's related to that. We will use a method called Newton-Raphson method. And to make that happen, we have to have an information about how is that we can find convergence of the unknowns, these ones. And that will be carried out with help of a Jacobian matrix. But this time you hear me like Jacobian matrix, you don't understand what I'm saying. You hear me, but you don't understand. Completely fine, because it's not the idea that you learn it and you understand this time, but later today, everything becomes clear to you. You will figure out everything today. Maybe not everything, but things related to these kinematics and multibody system dynamics, that will be clear to you end of the day. Promise you that. Okay, so then I have quite a few slides. By the way, YouTube officer, how is it? How this goes out? Is it? You check it earlier. So is it good? So it's no echo. The voice is clear and loud enough. Yeah. Good. All right. So I have quite a few number of slides, related to summary what we discussed last Monday. The first item that we discussed last Monday was related to Euler angles. And the concept of Euler angles is based on 3 successive rotations. So one rotation after another rotation after another rotation. So we have 3 successive rotations. And again, it means that once rotated coordinate system will be rotated twice, and then third time, and then you will have your final configuration. That's what the successive rotation stands for. All right? Well, we learned last Monday that one of the often used sequence of rotation is based on the sequence Z, X, Z. You may argue that, is this really the best sequence of rotation? Well, it of course depends, but it's often used, and it really doesn't make much difference if you change the sequence of rotation. Because no matter how is your sequence of rotation, you can put your body to any orientation in space. And also, if you're using 3 parameters to describe the body rotation, you end up dealing with the mathematical problems, which is typically related to singularities. In case of Euler angles, it is something that is called gimbal locking. Gimbal locking is not the physical lock. It's not like mechanism that locks something, but it's the fact that sometimes when using the Euler angles, it is difficult to differentiate what rotation is what. And that's simply because it's possible that the rotation takes place around the same axis. You cannot differentiate that any longer. I'm going to place a YouTube video about gimbal locking to you. So if you want to take a look at that, I think it's quite entertaining and educational as well. So gimbal locking. Remember that. Okay, anyway, so I was about to explain that we have 3 successive rotations. So first rotation was taking place around z-axis, and amount of rotation was this C, V. What is this? Phi. Okay, so phi. So first rotation is amount of phi. And then once we have one rotated coordinate system, then we're going to introduce another rotation, this time around x-axis. Amount of rotation is theta. All right? And then 2 times rotated coordinate system will be rotated one more time. Again, this time it will be rotated around 2 times rotated z-axis. Amount of rotation is this C, V, psi. Yeah, who cares? You know, it doesn't really make much difference, but the first amount of rotation is this. Second is clear, that's theta, that I know. Third one I don't know, but that doesn't matter. But anyway, so these are the amount of rotations. I guess that they're different, they're calling different in the different languages, are they? Like in Finnish they are calling different than in English? No. Maybe, I don't know. Anyways, I don't know what they are in Finnish either, so that's fine. Okay, so Team France will help me, no? No need to help me, so I'm fine. All right, so what we're going to do then is we're going to describe these 3 rotations mathematically, each one of them. So this describes the first rotation, this is a second rotation, and this is a third rotation. Once you're multiplying these matrices together, then you will have a final representation of 3 by 3 rotation matrix based on Euler angles. Clear? Let's practice. So I have a body that rotates 90 degrees. That's b divided by 2. Around the vector that is described here. So this is obviously a unit length vector, so I don't need to normalize that. And if you look at this vector, it seems to be axis of x-axis, because the first component is 1, and then the rest are zeros. So this is obviously x-axis. How can I introduce the rotation like that? Well, it's all about how can I select these 3 parameters, these Euler angles, the famous ones that I don't remember their names, how to call them, except the middle one that I remember that's theta. Okay, how much I should make a rotation in about the first z-axis? 0, because I don't need to rotate the system around the z-axis, but around x-axis. All right? What about the second rotation? How much is that? That will be p divided by 2. Why? Because this is exactly where the rotation takes place, around the x-axis. What about the final rotation? That will be again 0. You substitute that information to this equation. This is how it's going to be. So this is going to be our final 3x3 rotation matrix. Why is that I'm explaining you this? Well, first of all, that you can have a little bit of understanding how the other angles performs. But also, you know, next weekly assignment is a big puzzle. It's a big puzzle because I'm asking you to introduce the rotation around y-axis. So I'm saying that, okay, so why don't you introduce the rotation around the axis that was expressed like this? The good news is this. Good news is this, that if you look at this vector, this is supposed to be transpose here, this is unit in a length. So no need to normalize that. But that's about the good news. So then comes difficulties. Because how you can introduce the rotation like that, because you don't have it. I mean, that you only have a rotation around z, and then you have a rotation around x, and a z again. So obviously, y is missing. So is this like, no can do? Not possible. No, you're supposed to say yes or no.
Yes.
Yes, not possible. Possible. So it's possible. Okay. So how this is possible? Well, it will be possible in such the way that, look at this carefully, look at this first picture carefully. What we need to do in case of first rotation is that we need to introduce an amount of rotation that takes x-axis to position of original y-axis. That's how it's possible. And then where the y-axis is then pointing out, roughly here. Okay. Then, so the first rotation will be p divided by 2. Then you're ready to introduce your rotation. Whatever it was amount.
30.
Oh, how much that is in radian?
Pi by 6.
P divided by 6. All right, so the next one is p divided by 6. That's the real rotation you wanted to introduce. Okay, almost done, almost done. But remember what you did in the very beginning. In the very beginning, you made kind of like arbitrary rotation or assisting rotation. Assisting rotation, I figure that's the better word. So assisting rotation to make it possible to introduce this rotation around the y-axis. So obviously, what you have to do next is that you have to compensate this first rotation by, how you can do that? Minus p divided by 2. That's it. So it's solved. All right? Comfortable? Is this too much helping? It is, because, you know, here is a solution for you. But that's all right. Did you get the concept? No, the right hand. You got it?
Yes.
Yeah. Like,
From there it's more clear.
yeah. I think it's better to make a drawing because, you know, if you got like a stretch in your hand, I'm not responsible of covering that. So you can make your drawings, so it's going to be more safe. All right? I got the email from Jarkko. Jarkko is the person that is checking your weekly homework, and he sent your greetings as follows. So he said that be careful with the radians and degrees in the case of sine and cosine, well, trigonometric functions. This really depends on what software you're using and how are the settings in your software. But be careful with that, because if there's a need to enter radians and you entering the angles, it will be a big mess, like is other way around too. So careful with that. And then also double check that you're using correct submission box. Submission box is the one that you can find in a Moodle website. the module's website, you must be sure that you're using corresponding submission toolbox, submission box. If not, it's going to be very involving for us to figure out what is what. So be careful with that. And if you need help, just send an email to Jarkko. So those are my advices. Still more stuff to cover from the last week lecture, but I'm going to be brief only because there is so much exciting things coming soon. So we look like how is a velocity. Velocity you can get by simply taking our description of kinematics and differentiating that with respect to time. That will automatically give you velocity. This is very mechanical work, so it's just a pure mathematics. No thinking, no thinking. Just follow the mathematics. Once you follow the mathematics, you will get the expression as shown here as a particle velocity. This equation consists of two parts. First, I have here translation of velocity of body reference coordinate system. And then I have here angular velocity of the body reference coordinate system. And then I have here rotation matrix that is differentiated with respect to angle theta. Remember, this is like almost like original rotation matrix, except this is rotated 90 degrees, or p divided by 2. Maybe better to say p divided by 2. Maybe 90 degrees better to get, have a better understanding how it is. And then I have here vector u bar. Acceleration you can get by differentiating this equation one more time with respect to time. Now, something a bit surprising comes up when you do that, because acceleration is no longer consisting of two components, but instead it consists of three components. What are these three components? First of all, I have here translational acceleration of body reference coordinate system. That's easy to understand. It means this, like this, and this, and this. So this is translational velocity. And then I have here translational acceleration, and then I have here angular acceleration that is related to pure rotation. And then I have one more component here. This is tangential acceleration component due to the rotation. And then I have the component in the middle, which is a normal acceleration component that is quadratically related to velocities. Now that's not good. I mean, that's a little bit of bad news for us, because we have to use this equation in order to define the dynamic equilibrium. Generally speaking, it can be expressed like this. So I have external applied forces multiplied by mass of the particle, is equal than the mass of the particle multiplied by its acceleration. So when you do this, and when you express inertial forces, which is this one here, using generalized coordinates, there will be a component that is quadratically related to velocities, angular velocities. We will get back to that, but just already this time, try to adapt your mind to handle that bit of the surprise. Okay? And then we learn like how is that you can compute the number of degrees of freedom. This is very simple equation. You just need to know how many generalized coordinates you have in your system and how many constraint equations. Still simply subtracting number of constraint equations from the number of generalized coordinates. That's it. Or another way around. So that's it. That's how it goes. We can have three different scenarios. We can have over-constrained system where the number of degrees of freedom is less than 0. System is unable to move, like is the case here. So I have a crankshaft mechanism where connection rod is connected to ground. This cannot move because we are dealing with rigid bodies. So there is no mechanical deformation. So nothing will move. No particle will move because of constraints are introduced like that. And then I have kinematically driven system. That is the one we're going to look carefully today. So that's the one where the number of degrees of freedom is equal than the 0. So we have equal number of constraint equation than the generalized coordinates. That's it. So we can solve the response by using just constraint equations, nothing else. And then I have dynamically driven system where there's a force imposed to system. You have to create the equation of motion and solve that with respect to time or in forward of time to solve the response of dynamically driven system. And then Reta sent me an email sometimes last week. She was able to discover that there was a serious typing mistake in my slide. You were doing this all the time, like everything fine. Go ahead, Aki, everything is, correct and everything. It wasn't correct. There was a serious typing mistake because it was written like this. Look at this. Cosine. Please, this is supposed to be obviously, this multiplied by this gives you this row, this multiplied by this. Oh no, this is supposed to be, of course, sine. More problems. This supposed to be y, of course. And, this supposed to be minus sign. So this is how it's supposed to read correctly. Did you notice? I guess that you noticed it, but you were just, let's see how long it takes that Aki can figure that out. Right? Okay, constraint equations. So these are the different kind of constraints. Excuse me. Different kind of constraints you can find in a planar case. So what are the number of constraint equations you need in these different cases? So first I have fixed joint, meaning that the body is attached to ground. How many constraint equations you need to make that happen? Well, obviously, you're constraining all possible motions, so you need 3 constraint equations, right? So what about the revolute joint? That's something that we learned already last Monday, and we learned that you need to have 2 constraint equations in order to introduce revolute joint, right? Then translational joint, how many constraint equations? 2, because it leaves 1 degree of freedom that is sliding with respect to each other. And the primitive joint is 1. How is this primitive joint? So this is the one that the body can go up, so it can move along the global y-axis, and it can rotate. So it's like a slot, some kind where this point is sliding, so it can go up and it can rotate. A little bit of bad quality joint, but you got the idea. So 1 constraint equation is needed. So if you have one body that is connected to ground with primitive joint, it's going to have 2 degrees of freedom. Okay? Clear? So what are the number of degrees of freedom in these cases? So my advice to you to compute that or solve the problem like this is that you're first going to take a look how many moving bodies you have in the system. So let's get started from this one here, this system A. So how many moving bodies I have in the system? So it's 1, 2, 3, 4, 5, 6, 7. When are you gonna stop? Okay, so let's go back here. How many moving bodies I have? I have 1. That's clearly a moving body, correct? And then I have here piston body, which is second. Kind of like a piston body that is moving. This box-like body is moving with respect to this beam-like body. So the beam-like body, this one here, that's my third body. So I have a total of 3 moving bodies. 3. How many generalized coordinates I need to describe this system, fully describe this system? 9, correct. So that's 9. Okay, So how many constraint equations I have? So let's first compute the number of revolute joints. So I have 1, 2, 3, no, yes, no, yes, yes, because it's, look at it's dot. No, it's not the one. You know, of course it's not, you know, revolute zone, because what is the body that this connects with? Nothing. You know, this is the kind of the thing that I do a lot in a written exam. You know, trying to make you feel confused. I don't know, is it like hilarious? Is it funny? No, not funny. Not funny at all. A little bit funny. Not much funny. Okay, so what I have here, 3 revolute joints. So I have, and how many equations I need? That was 2, so that's 6. And then what about this one? This is a translational joint. So let's put it this one, let's add that. So there's 1 translational joint, that's 6, that's 2, so that's 1 degree of freedom. Oh, okay, so maybe there's a little bit of delay. Let me see. Connection is, you know, the Eduroam connection is very weak down here. I'm sure that it's much better up there, but here, down here is no good. Is it coming or not? Let's see, I guess that I need to reconnect this. Yeah, it's frozen. It is still mirroring my screen, so maybe I'm going to reconnect this to see what happens. Oh, it's coming back. But the writing is not coming. Okay, let's try this. Ah, so yeah, the connection is lost. Yeah, connection is lost, so I need to reconnect this. So it's going to take me 30 seconds to do so. QR code. Yeah, connection is not good. Now it's back. Good. All right, so it's coming back. And here is a writing too. Not yet, but soon it will be here. It's connected, so it should be fine. Is it somehow related to this PDF? Okay, this seems to be fine. So let me soon. By the way, very soon there will be a Socrates question. Okay. There is no other way than restart the PDF. Still no. God damn it. You see nothing now. So when that disappeared?
Just now.
Just now.
Okay.
So it's getting worse, much worse. How come I don't get this thing? So I should do what?
When you place that, you might have moved one of the cables.
This, so this cable? No, the cable seems to be all right. Should I? This place is haunted. This place is really, there is really something wrong in this place because, you know, look at this. So no, nothing goes out. Huh. Okay, now it's back. So at least we have that much. But still I'm not happy because, you know, look how is our server. Mirroring. So maybe I need to look at that. Yeah. So I need to do one more connection, and hopefully this is the last one. Gonna close this. Okay. QR. Okay, it's connected, so it looks promising. Okay, everything looks good. And look at this. Come on. PDF. I don't understand why it is not showing any PDF. This is really, really hard to understand. Maybe I can use another software then. What that could be. I don't know. PDF export. No, I don't want to install that. Okay, so what we need to have is that we have to have a 5 minutes break, and during that break I need to figure out like what the heck is going on with this device. And so let's have a break and make sure that you're ready with the in-class quiz because you know there's a one coming in the next slide, and it is related to computing the number of degrees of freedom. So be ready for that. So 5 minutes break, hopefully even less than that. So go stand up, stretch a little bit, breathe deeply, and be ready for in-class quiz. All right? Okay, so online participants, I'm gonna stop the, well, I'm not gonna stop the streaming, I'm still gonna keep it on. Hopefully, I'm able to figure it out what's going on here. I don't see any other way. I just need to restart my computer. So back in the streaming mode. Still experience a little bit of technical difficulties, so hopefully it is running. Where it is running? I don't get it. Look, yes, I'm a Superman. I get along with the computers really, really well. All right, so good. So we just keep on going right away. So because I know that all these technical difficulties takes longer than it's longer than I expect. So let's just go. So here are the numbers that I put it in a writing in just before these technical difficulties. So I have again a total of, hold on. So I have a total of 9 generalized coordinates. Then I have 3 revolute joints. Each one of the revolute joints, they need 2 constraint equations. 2. All right? And then I have 1 translational joint. So when you do the math, when you put this all together, that's going to be a total of 8. 9 minus 8, 1 degrees of freedom. So it can move one way only. What about this? Let's get started from what's the number of moving bodies? 44. 4? 4. Any other votes? 2? What is it? 4. 4 is correct. So here's a winner. So, so that's the winner. So how this is a bit confusing because obviously I have here piston body and a cylinder body, which are connected together with help of translational joint. All right. So that's 1, 2, 3, 4. So fourth body is almost invisible. All right. So I have 4 bodies. What about the joints? How many? Let's get, so again, now I have 4 bodies, so how many generalized coordinates I have in the system? 12, correct, so that's 12. Now let's just compute it. What's the number of translational joint first? 2, that's 2. And I need 2 equations to describe translational joint, so it's 2 multiplied by 2. All right? But I have also revolute joint, revolute joints. But how many? How many revolute joints I have? 3. 3 is correct. Yeah, I'm sorry, I don't know why I have this habit that I want to make you confused, feeling confused. I'm really trying to work with me to get rid of that. Sorry about that, but it's 3. 1, 2, 3. Okay, so what it means, so I have 2 constraint equations multiplied by 3. So that's 4, that's 6, that's 10. 12 minus 10 is how much? 2. 2 different ways. It can move in 2 different ways. I have no idea how is my camera, but 2 different ways means that they can go downwards, and then they can kind of rotate like this. You got it? So they can go, they can extend simultaneously. Then this point goes down, or one can extend, another one extract. So then they kind of rotate. You got it? You understand how is this way? Okay, let me ask you this. Yes, sir.
The first one, 9, 3 bodies, so 9.
The first one, okay, 3 bodies. Okay, so 3 bodies is 3 multiplied by 3, so that's 9. And then the number of revolute is 1, 2, 3. So that's 3 multiplied by 2 plus 1 translational joint. That's how it goes. Clear? Okay, what about this? What's the number of degrees of freedom? What's the number of degrees of freedom? So to answer that question, first, remember to compute how many moving bodies you have. All right? Then remember to compute how many revolute joints you have. Then remember to compute how many primitive joints you have. This is equation to compute how many constraint equations are needed if you are dealing with a primitive joint. Okay, so let me put the Socrative on. So this one, and you're good to go. So it's on. So I have already 53 students. So it seems, by the way, that most of the students are physically here because I can, it's like, 40, oh yeah, you need to see the picture. Is this one? Oh no, this one. This is the question. I'm thinking, you know what I'm thinking that's going to happen today? I'm thinking that yes, it will be 100% success rate. 100%. Yes, you hear me correct. 100%. It will happen today. You don't believe so? So think about this.
One is primitive, one is revolute, 2 are revolute.
No comments. I cannot give you any comments. No comments. No comments. But don't, here's my advice to you. This goes to particular Team France, is looking this in a different, incorrect way. Don't think about it, what are the different ways, because this is not that complicated question. Compute what are the number of moving bodies and compute what are the constraints. Don't think. Remember, multi-body system dynamics, what is not allowed? Thinking. Thinking is not allowed here. So mechanically. Do mechanically. Don't think. You got it? No thinking. Absolutely no thinking. All right? Clear? Okay, you want to have some time to think about it, or you done? Let me take a look. Now this seems to be very, again, YouTube office. So don't think about the way it can move. Compute the number of bodies, compute the number of constraints. That's it. That's it. Because as soon as you started to look at what are the possible ways it can move, I'm sure you can do it when the mechanism is this simple. But as soon as it becomes more complicated, you cannot do it anymore. So don't think about it that complicated way. So it's simple. Okay, are we done? So let me take a look. What is this? So I have one student that answered. No, it's correct. So 82 students and 61 already entered the answer. 63, 20 are still thinking. Can I just go? Can I just release what is it? Okay, I'm gonna wait, say 10 seconds. 10 seconds. So in 5, in 4, my clock is a bit slow. In 3, okay, so 4 are still thinking. So final 4, because I want to see this, because I'm thinking that this is going to be that exciting time in my life when I'm going to get 100% success rate. Okay, so 4 are still thinking, but I'm going to close this right now. So this is it. Okay, what is your prediction regarding the success rate? What? No, one, that's way too low. So it's going to be 100%. Okay?
Oh,
Okay, so let's go back to, it's just life, you know, the life is like, it's a wave motion, it's like vibration. So sometimes it's not that successful at other times. Okay, so let's compute this together. How many moving bodies I have? 2. No, 2. 2 moving bodies. So it's how many generalized coordinates I have to have? 2 multiplied by 3. Everybody have to have a 3. Everybody have to have a 3 what? Generalized coordinates. So it's going to be 6 minus. And then let's compute how many revolute joint I have. 2. 2 multiplied by 2 plus 1 primitive joint. That's 1. So you do this math, that's going to be 6 minus 5, 1 degrees of freedom. 1 degrees of freedom.
I thought that was also primitive.
Which one? This primitive joint? No, it's a revolute joint. Okay. All right, so these are the different names. I'm not so worried about the names because, even if you would memorize this, you're still going to forget this zone. But let me just I would like you to know that we typically deal with the holonomic constraints. Those are the constraints where, I'm using, equal something, and it's depending on, or it's a function of generalized coordinates. Non-holonomic constraints are the one that are function of generalized velocities, and they may involve inequalities. We are not going to touch this type of constraints. But if you have to deal with, say, rolling without slipping, you have a coin that is rolling without slipping in a 3-dimensional surface, you can describe that by using non-holonomic constraint. Bicycle, which is another possibility that you can study with the multi-body system dynamics, the bicycle wheels have to be described by non-holonomic constraints. By the way, guys, I need to, guys in the back, you need to be quiet because I'm using this low quality mic and it's getting all the noise. So you talking goes all the way to, goes to YouTube, and then everyone can listen to whatever you're talking. Okay? All right, then I have, I don't know how to pronounce, it's also possible to have a very complicated word, scleronomic, whatever. It's the same thing like this phi, but this just to get you to know that this is the one that is a function of generalized coordinates only. Rheonomic, which are driven constraint. This is something we will deal with in this course. We will deal with this type of the constraints and this type of the constraint. Rheonomic constraints are driven constraint, something that you introducing the kind of, you're forcing system to move in a certain way, and those are called rheonomic constraint, driven constraint. There will be examples coming soon. All right, so then shortly, another thing like how things are in a 3-dimensional space. These are from the Atom software, and based on the Atom software, there's a matrix that tells how many degrees of freedom are removed when different kind of 3-dimensional joints are used. These are the joint types. So it's like revolute joint, which is here, revolute joint, shown here. So it's removing 3 degrees of freedom, 3 translational degrees of freedom, and 2 rotational degrees of freedom. This is in 3-dimensional case, in spatial case. Then translational joint, it's located here, so it's removing 3 rotational degrees of freedom and 2 translational degrees of freedom, so on and so forth. So this matrix tells you how different 3-dimensional joints are eliminating the motion possibilities. This too is a figure from Atom software. It is also possible to use something that is primitive joint, which is kind of ingredients, components of joints, and these are the one you can combine however you want. Joints itself, this is by the way very, very important to understand. joint itself, you cannot combine because you end up to have a difficulties, something that I will explain in the next few slides. But this primitive joint, which is kind of like a component of joint, you can combine them however you want. Okay, let's look how is a case if we would like to model a behavior of the door. You know, the door is a system that consists of one moving body. And this is let's consider this as a spatial case in three-dimensional space. All right, so I have one moving body. This is my one moving body. So how many generalized coordinates I need in order to model a door? 6. 6, because this is a spatial body. All right, then I'm introducing here a revolute joint. Now, how is going to be how many constraint equations I need in order to introduce the revolute joint? So it's 3 plus 2, so that's 5. All right, so it's going to be 6 minus 5, 1 degree of freedom. Seems to be fine. But if you look at the door up there, it's not actually consisting of one revolute joint, but 2, sometimes even 3. So let's look what happens if we are not using one revolute joint but many revolute joints. Okay, so how many moving bodies I have in this case? 1, nothing changed. So I have 6 generalized coordinates, and then I have here one revolute joint, another revolute joint. So that's 5 multiplied by 2, 10. So it's going to be 6 minus 10 minus 4. So we are locked. You see, because if we go all the way here, remember, where is it? Where is it now? How? Oh yeah, here. Over constraint, not possible to move. So this is it. So we cannot escape from this lecture room because we are stuck here. Because it was just mathematically proved that it cannot move. Any last wishes, or this is it? So this is it. Dead end. What?
The ones in series.
They are in series. So they are in series. Yeah, actually that is the right thing. There are, the thing is that in order to understand why the door is still capable to perform, we have to look, how are these constraints? Are they independent or are they depending on each other? And now I'm constraining the same generalized coordinates, so they are not independent constraint equations. So if you look at the lecture notes, it says this very important word which is independent constraint. So the general form constraint equation can be expressed like this. The independent constraint equations are, so they have to be independent. And if you model the door like it is modeled, in that case, they are not independent, but they are dependent on each other. So they are not the way they are mathematically intended to be. Many of the commercial multi-body softwares, they can recognize that they are dependent coordinates, dependent constraints, and they can automatically eliminate some of them. But my recommendation to you is not to model the system as a redundant system. Try to model such the way that you not end up to have dependent constraints, because otherwise it can be considered as a very poor modeling policy or modeling practice. So try to avoid something like that. In three-dimensional space, it's not at all easy to avoid it. And let me tell you why. Because if we look at the 4-bar mechanism, 4-bar mechanism, I have here 1, 2, 3 moving bodies. So I have 6 multiplied by 3 generalized coordinates, so that's 18, right? Okay, so 18 minus how many revolute joints I have here? 1, 2, 3, 4. All right, so it's going to be 5 multiplied by 4. How much is this? 20. So it's going to be minus 2. So it's redundant system. So look how easily it happens. So you just may thought that, this is all right to do it, but, the motion in a, whatever is this direction, is it Z direction, is over constrained. There is too many constraints to that direction. You don't need that many constraints. So instead of modeling this by using a revolute joint in all the corners, this should be inline primitive joint. Primitive joint. Because, when you have this system here, this end cannot move in this direction any longer. So you don't need this additional revolute joint. You following me? No, you're really, really confused. Like, really? Another important thing is that, the joints we are dealing with are ideal joints. There is no clearance. No clearance whatsoever. They are mathematically ideal. No clearance, no friction. They are just perfect joints. Now that's a very different what you can find in a reality, because in reality you have a friction and you have a clearance and you have a deformable bodies, but we don't. We have no deformation whatsoever. Okay? Clear? Can you do this? Am I forced you to do this? Yes. Because I would like to do this. But I don't want to do it because my fellow student is doing this. Yes. No. All right, so we can get back to this if you want, but let's practice a little bit more about how are the constraint equations. Now this is a system which consists of one moving body, and now this one moving body is constrained to ground with help of two primitive joints. Two primitive joints. The first primitive joint is located in a point P, which is up here. Another one is point O, which is down here. How the system can move is that these both points can slide along this sludge, and that's it. So it can move. How many degrees of freedom I have in the system? One, because I have one body, so it's 3 generalized coordinates because everybody needs 3. And then I have 2 primitive joints, so it's 1 degrees of freedom. Right? How can I model these primitive joints then? How is possible to constrain in such a way that they are sliding along the global y-axis, like this one here, but not moving this direction? Of course, what I'm going to do again is I'm going to take the use of the one equation that we are very familiar with, this one. And then with help of this equation, I'm going to introduce the motion limitations. Simple like that. Okay, so and here is my global coordinate system. So first I'm going to introduce my vector r, which is this one here. And then I'm going to account the orientation of body reference coordinate system with help of 2x2 rotation matrix. And then with help of vector u bar, I either travel here or here, depending what is that I wanted to constrain. And then I simply introducing the motion limitation to this equation. So look at this. So I'm repeating over and over again this very same equation, the one you are very much familiar with. Okay, so would you like to see the details? No? Still, I'm going to show the details to you. So it goes this way. So I'm going to first take a look at where the point O, this one, where that is located. Always I have to start from the origin of the global coordinate system. And always I have to travel via body reference coordinate system. Always. There's no other way. Sometimes it's possible, particularly in a written exam, there's a case where there's a, let's say, a pendulum like this. The pendulum global coordinate system is located here in where the revolute joint is located. Still, you cannot jump to this position without traveling first the body reference coordinate system. So you first need to go here and then back with help of vector u bar. So never ever take a shortcut, but always travel via body reference coordinate system. Okay, So let's travel via body reference coordinate system. So we go here. So we have here this translational component. Then I have the rotation. I don't know what is current configuration, but I have this 2x2 rotation matrix. That's fine. And then I'm traveling to this point. How can I do this traveling? I need to just introduce the vector u-bar, and that's the only place where you need the moderate amount of thinking. Moderate, not heavy thinking, because as soon as you have started to have a heavy thinking, you will make a mistake. So moderate amount of thinking. How is the vector u-bar? So look at this. So the x-axis is pointing this direction. Can you see this? So I cannot make this any bigger, but hopefully it's clear enough. Okay, so can you see that x-axis is pointing this direction? So we first go here, and then vector u-bar must be L divided by 2, 0. Why 0? Why the y component is 0? Because we don't need to travel in a global in a body reference y coordinate axis at all. Clear? All right, so then I have this equation. This is how it looks. Then there comes the constraint. So what is that I wanted to constrain? I wanted to constrain the motion in a global x direction, such the way that this direction or this length will be amount of d no matter what. So I'm just saying here that this component have to be equal to d. The d is what? Is this distance. All right? So I'm doing the math. I'm taking this component, I'm multiplying this with vector u-bar, like shown here. Let me just check that there's no mistake. And then my d, I'm going to take a d and put it in a left-hand side of the equation. Put this all equal to 0. That's my constraint equation. Yes. Can do attitude. So it's possible. Look at that. So we already described such a complicated joint, primitive joint. No difficulties whatsoever. A little bit of difficulties. Now we can discuss about those difficulties. Comments? No? Is this clear?
Can you explain that d part? How is equal to d?
Yes. Let me explain the d part. Thank you so much, because let me think what are all the students, every single one is thinking like, what the heck is this d? I really would like to ask what is this d, but I don't dare, because then others are looking that I don't get it. No one is understanding this. Even myself, I'm like, what is this d? Like how this goes? Like what are the concepts? So this is difficult. But let's look this together. Maybe we can solve this together. Okay. So let's look at the big picture. So we have here this point O, this point that we can describe by using this equation. Now what is that we need to do to that point? We have to say to this point that this point you can do whatever you want, except you cannot move along the global x-axis. You have to stay in a position which is equal to d no matter what. You have to remain in this line. So this component have to be equal, the low quality drawing, this component have to be equal to d no matter what is happening in the system. That's what the d is standing for. So this can go up, it can go down, but it cannot move to this direction because it is constrained with help of the d. Of course, d is reality is a number. It's like 10 meters, 2 meters, 10 centimeters, but that's what it is. You got it? Can we now do this? Yes. Okay. What about the other constraints? How we can do that? No surprises. We're going to follow the same procedure again. All right? So we're going to simply take the same equation. This time, the only difference is that the vector u-bar have to be different because we are not going here, but instead we're going here. Other than that, the journey will be same. So we're traveling here to body reference coordinate system, and then here we're traveling to this point. How can I make that happen? Well, it's going to be minus L divided by 2. Minus because I'm traveling to minus direction from the origin of the body reference coordinate system. Clear? Y is equal to 0. And now I'm saying the same thing. You know, it can slide along this line, but it cannot move along the global y-axis other than the amount of A. That's it. That's my second constraint equation.
If that was 1 meter, so
If this would be 1 meter, this would be minus 1. And it will stay in that particular location no matter what, all the time.
if this, what is it, pendulum or something?
No, this is not the pendulum. This is like the system that moves like, it's a little difficult to describe.
Maybe that the rod, can we say rod?
Kind of. In order to figure this out, let's model this in the end of the class so we can see the response. Right now we don't know because we just don't know.
So if the length of the rod from a primitive joint to other, that length is 1 meter, if we go upwards, so would it be minus 0.5 meter?
Minus 0.1? Of course,
0.2.
of course. But it needs to be physically possible. You know, of course, you know, if the length of the body is 1 meter and I will take this constraint really way off, then it's not possible. So it has to be something that is feasible, something that the body can fulfill this requirement. Okay? Makes sense? Okay, so, here is in-class quiz. Now, please, before we go into this, I hope that you have learned one thing. The one thing is that the particle do not rotate. Particle do not rotate. Why? Because it's particle. It is particle. It hates rotation. So it's, you know, it's an enemy of rotation. So there's two things that they never ever get along is a rotation of particle. All right? Now my in-class quiz is this. Constraint equation. Question mark. What is a constraint equation? What is an interpretation of constraint equation? It interconnects generalized coordinates. It defines the body configuration in the global coordinate system. It defines the physical dimension of body. It defines the particle rotation in a global coordinate system. Only one is correct. But which one? This needs to be, you have to have some serious thinking in order to answer that question, because remember the mathematical definition of constraint equation. I need to go back here. No, here. Look what it is doing. It is focusing on something. This is what it is focusing on. So it's applying something to this set of coordinates. That's it. Nothing else. That's the role of the constraint equation. So let me put the Socrative on. Next one. So here is a constraint equation. So again, the same. The options are interconnect generalized coordinates, defines a body configuration in the global coordinate system, defines the physical dimension of a body, defines a particle rotation in the global coordinate system. One only is correct. Here are the choices again. Oh, no, not here. Here are the choices again. So, what should I do? Should I help you a bit more? Or is this clear? It's not clear. You need a little bit more help.
Yes.
Okay. So, what is that we have discussed about? Maybe we can eliminate some of the really worst options. Particle rotation is out. Then dimension of body leaves just two options. the key word is this. This is a single body. And really, what we wanted to do is that this is, the system that we are looking at. Not the single body, but the system. And look at when we look at the mathematical definition of constraint equation, is this one. Let me remove this. So it's introducing something between generalized coordinates. That's what it's doing. Clear enough? All right? So with that, is this cheating now? If we're now going to get the 100%, I'm not going to be happy about that. I will hate myself. Because it's like cheating. This is cheating. But it's not going to be 100%, so I can be very relaxed about that. Because still, some people are thinking that maybe still the particle can rotate. And that's it. Okay? So let me see. We have 75 students that already entered their answer. You need some more time, or you done? $81. What was the number last time? I think it was 86, something like that. And I'm sure many of them fed up already and they left. 83, so let's weigh the, okay, 88. So we have more participants. How come? 88. Okay. You ready? In 5, 4, 3. Okay, now it's not changing, so I can just close this. Good, very good, very good. But what worries me is this. Still 2% was voting that the particle rotation in the global coordinate system. Okay, so let me make this clear. Particle hates rotation. Particle is not rotating because it's a particle. So that's off the plate. Physical dimension of the plate, 2% was voting that too. Nope. Excuse me. So that's also very incorrect. This, body configuration, there's a little bit of truth here, but really what it's doing is interconnect. Is introducing the connection between the generalized coordinates. And that's what is called motion limitation. Motion limitation. All right? You want to complain, or you just happy my scoring system? No complaints. Okay? Now comes a little bit of painful part, because I would like to shortly explain how is that you can introduce a translational joint. Now this is, mathematically, this is unpleasant, very unpleasant. And I'm thinking that we can go over this, but not looking too much about the mathematical details. Why not? Because you only need to deal with the translational joint if you're going with, this paper written exam, the one that is covering the full course. And this is what I can promise as well. If you go the first written exam, you don't need to deal with the translational joint, but you go the second or third, for sure you can see that translational joint. So that tells you a bit how difficult is this constraint. So let's look at this carefully. We concluded previously that this is a constraint that needs two constraint equations. So the first constraint equation is very simple. It is limiting the relative rotation between these two bodies. So once you introduce a translational joint, the translation of the two bodies, the relative translation will be eliminated. So that's the first simple constraint. How you can do that? Well, it's simple like this. So you have the angle of the first body, angle of the second body have to be equal than the constant. Constant, means that maybe there's an angle difference between these two bodies. Often, the C here is equal to 0. but it can be any random number, so it can be something else other than 0, because the angle difference can be whatever you want. All right? Then comes the difficult part. Now they cannot have relative rotation anymore. But next, what I'm supposed to do is that I'm supposed to introduce sliding, relative sliding between these two bodies. Obviously, if I have this box-like body, this one here, the box-like body can slide along the beam-like body in such a way that it goes along this line here. This is mathematically a bit involving to describe, and that's what I'm going to do next. So, to make that happen, I'm introducing 3 points. Now the first point belongs to beam-like body and is a point O. Right? Second one will belong to box-like body and it will be called P. And then I'm going to introduce one more point which is perpendicular with respect to line from P to O, or O to P, and that point is Q. Is again perpendicular, so there's a 90 degrees angle difference between this line and this line. All right, now this is almost everything that I need, because what I need to do is that, let me take this off again. I need to describe a vector that starts here and ends here. How can I do that? Well, again, surprising enough, I'm going to use the equation that we are very much familiar with. So this is going to be the starting point, and I'm going to describe this one here, and then I'm going to look at where is the ending point. It will be a different body, but I'm just going to repeat this equation that I'm very much familiar with, like this. This is body, what is this body called? A body. Oh my God, my writing is like unbelievably bad. But you got the concept. And this is, this is B body. Is it B? Yes, it's B body. Here is B. Okay, that's it. That's my line. And then I'm introduce another line. This one here. So I'm going to have another vector. Using perpendicular condition, mathematical condition, that's my constraint. I'm just forcing these two vectors to be perpendicular all the time. So it's going to be vector multiplied by vector, vector dot vector. It's going to give me a scalar quantity. Following me? That's all right, because, let's look at that in the details, and then while we look at the details, I'm going to try to explain this again. Again, I have this point O and P. Let's write that vector first, from O to B, how it's going to be. So it's going to be such the way that I have here, O minus B. That's what I just explained to you. How is this? So first I'm going to travel the body reference coordinate system of body A. It's here. Then I'm going to count the orientation of body reference coordinate system with help of 2x2 matrix, and then my vector u bar, which happened to be 0, because I'm in the origin of the body reference coordinate system. And then I will do the same, but this time for body B. So I'm going to travel first to body reference coordinate system. I'm going to count the orientation, and with help of vector u bar, I'm going to end up to be in a point B. So my vector is going to be the one that is shown here. The B vector, or the H vector, that is the one that is perpendicular here, that remains within the body B. So it's much simpler to describe. But again, I'm going to do that in the same way. So first body reference coordinate system, then orientation, and then vector u bar, and then the point that is associated to this point here. So first body translation, orientation, and vector u bar, and that's what's going to be my final solution. Now I have two vectors that both having two components. Perpendicular condition, if you remember from the mathematics, will be multiplying these two vectors together, and if the solution is equal to 0, then they will have 90 degrees angle with respect to each other. You do this, and you have a sliding constraint. Can you make me a favor and do this? No, this is really, really difficult, and it takes a little while to understand the concept. Would you like me to repeat the concept? You don't like me to repeat it? I'm still going to repeat it. Again, we have 3 points. First point, O, belongs body A. Clear. You go and define that point with the equation that you are very, very familiar with. This equation. Right. Then you're going to define the point P, which belongs to body B. The same thing. You're going to repeat this equation, but this time with help of body B. This is going to give you vector. Right? And then you're going to look at another vector. Another vector you can get by defining how it is vector from P to Q. And this is within the body B. So it's much more simple to describe. Once you just follow that, you have 2 vectors, and then you're forcing these 2 vectors to be perpendicular with respect to each other. Perpendicular meaning 90 degrees. 90 degrees angle. How you can do that mathematically? Well, it's a vector multiplied by vector have to be equal to 0. This is what they're teaching already in junior high school. What they deal in vectors in junior high school? No? High school. High school they do, yes. So high school there's a vector multiplied by vector. If this multiplication is equal to 0, then they are having this 90 degrees angle. That's my constraint. Rest is mechanical mathematics. All right? So mechanical mathematics looks, by the way, really, really bad. But don't get confused about that. That's how the final details look like. And now if you wanted to simplify it, it looks, that's my final constraint equation. All right. So far, we have been looking at how is a simple system with, one moving body, how that can be constrained. And now I would like to introduce you this mechanism, which consists of 2 moving bodies. And I would like to constrain this, to introduce the constraint to this system. Why? Because later, this is the one that I will solve the kinematics. Now, how this is described right now, I cannot solve the kinematics because this is not kinematically driven system. Why not kinematically driven system? Because if you look at what is the number of degrees of freedom, is other than 0. But what's the number of degrees of freedom? I have 1, 2 moving bodies, so 6 generalized coordinates. And then I have 1, 2 revolute joints. And then I have here 1 primitive joint. So that's 5. So it's equal to 1 degrees of freedom. How is this 1 degrees of freedom? Well, it's a crankshaft mechanism. So it's this point here is moving back and forth along the global x-axis. Other bodies, which is body A and body B, are following due to the constraints. Clear? But I have 1 degrees of freedom, so this is not kinematically driven system. I could make this to be kinematically driven system by introducing another constraint, 6th constraint. And the 6th constraint could be saying that, okay, this point P, just hypothetically, there's many possibilities to do so, but I could say this point Q cannot move freely any longer, but it has to follow the certain equation. That's constraint. And then I have kinematically driven system. I have 6 constraint equation, 6 unknowns. That's it. But now let's look at how I can constrain this system. So let's get started from this point here, the point O. This is a good example where there's a temptation, heightened temptation to take a shortcut. Never ever take a shortcut. Okay, what is that we have learned so far? So we have learned that particle, we don't have a rotational degrees of freedom. Everybody needs 3. Everybody needs 3. So that's another big lesson. Everybody needs 3 in a planar case. 3 generalized coordinates. Then another thing is never ever take a shortcut. So we have 3 lessons. Never ever shortcut. 4th lesson is no thinking. Okay? We're done. We're good. Okay, so here is point O. This is where I would like to travel. So how it goes. So I have here global coordinate system, which happens to be exactly where this constraint is located at. Still, I have to travel first the body reference coordinate system, and then with help of vector u bar I can travel back. You always have to do this. No shortcutting. Okay, how it goes. I have here translation of body reference coordinate system, orientation of body reference coordinate system, and then vector u bar. How is minus L divided by 2? Because the x-axis is pointing this direction. So let me make this clear to you. So I'm first traveling from here to here. That will be described by this guy here. And then I'm accounting orientation with help of this 2 by 2 rotation matrix, and then I'm traveling back with help of vector u bar. That's why the minus L divided by 2. This has to be equal to 0, 0, because where this rotational joint is located at with respect to global coordinate system. It's on the origin of the global coordinate system. That's why this has to be equal to 0. Clear? This gives me, now when you do the math, it gives me 2 constraint equations. I need more. I can take a look at the point P, which is something that we're actually already familiar with. So we're going to describe the point P with respect to body A and with respect to body B. Once we put these to be equal, it means that this point has to be common to these 2 bodies, so they cannot separate once I have this constraint. Yes? Clear? Okay, so let's travel to this point P with help of body A. First translation to body reference coordinate system, then accounting the orientation, and then with help of vector u bar, I continue my trip and I reach my final destination, which is a point P. Then I will take the body B, gonna go first here, and then I'm gonna account the orientation, and with help of vector u bar, I go to my final destination, which is where the revolute joint is located at. Gives me 2 additional constraint equations. All right? Then my final point is Q point. I'm gonna travel that with help of body B. So first here, then orientation, and with help of vector u bar, I reach this point. Now this time it has to be L divided by 2. And I'm constraining, look at this. So I'm constraining the motion to y direction. So I'm saying that this guy here has to be equal to 0. All right? So I'm taking this component, I'm multiplying, this with this, and that's it. That's how is my 5th constraint equation, how that look like. Clear? Very clear. All right, you're ready to take the final step today. I know that it's a long day. That's mainly because of these technical difficulties, but still I would like to take the final step and look at how is a kinematic, how is that we can solve the kinematics. Maybe unable to do this week, but I have some unbelievably nice looking animation when we are solving this mechanism kinematically. So it's looking, I'm sure, I can make a bet that once you see this solution, you're gonna cry because you're so happy that you don't believe that by yourself. And it's all right to cry. Let the emotion to come up. Because, this is something that makes a difference in your life. Kinematic solution. There's life before and after kinematic solution. It's like, these big moments in your life, getting married, boy, this having the first child, and so on and so forth, and learning the kinematics. All right? Now, let's look at the kinematics. First of all, just a few words about how is a kinematic analysis. It's not that often used, to be honest. But it is used to figure out what is a workspace of a manipulator, because it can reach all possible corners. It can look at like how far it can reach, how it can be configured in different places. So it's used in that kind of purposes. But again, something very important to understand that is not about forces, it's all about motion. Remember, not a single word is mentioned about forces so far. We have not dealt with the forces, but constraints and motions, nothing else. All right, so sometimes it is used to look at like if there's a collision, if you do the assembly, you can see if things can fit together. That can be carried out by using kinematic analysis. But you cannot really figure out what the force is in your system while you do the kinematic analysis. Now, it consists of 3 steps. First, we have to solve the position of generalized coordinates. This is the first and most difficult part, with meaning that we have to solve vector of generalized coordinates. And it's not simple, because they are hidden inside of the constraint equations. So they are somewhere hidden there, but we have our ways to figure it out what are the generalized coordinates. Again, they are hidden to vector of constraint equation, which is a function of generalized coordinates. And this is what is that we like to solve in the very beginning, position level analysis. Once we know the position, then we can move on and we can solve the velocity of generalized coordinates. Always about generalized coordinates. Why? Because those are the unknowns. Those are really the components that we like to learn. We need to know how are the generalized coordinates, because otherwise we don't know the solution, we don't know the configuration. So the generalized coordinates we must solve. The final thing, acceleration. Okay, as you know, you have to take care of all these steps, because you have to update your equation. Sorry about that. So you have to, no, I got really confused. What was this talk about?
Mind the point.
Yeah, so, but what was this thing about multibody dynamics? Don't remember right now. Yeah, it was about like how, how things gonna, yeah, now I remember. So once you know your velocity, acceleration, and position, then you can go ahead and update your equations, which are constraint equations this time. All right, so once you have the constraints, rest is downhill. That's exactly what it is. So once you have an equation of constraints, that's it. Rest is mechanical mathematics. So rest is a polar plate. Simple. Repeating, no thinking. But getting constraints needs a little bit of, this manual work, like we learned just an example just a little while ago. All right, so this is a kinematic analysis. So here's the deal. So we have equal number of constraint equations than we have unknowns. Say in the previous case, we have this mechanism, but now I'm going to introduce one more constraint, which is forcing the point Q to follow certain equation along the global x direction. That would be another constraint equation. Now I have here 5 constraint equation, but that would give me 6th one. How many unknowns I have in my system? 6. So I have all this information to solve the system. Okay, so how it goes? So it goes such the way that I'm creating all these equations, and then I'm using the tools that I learned from the mathematics to solve the nonlinear algebraic equations or set of nonlinear algebraic equations. How you can make it happen? What was that? Yeah, so I can use the method that is called Newton-Raphson method. So it's an iterative method. So it's not giving me a solution right away, but gives me the direction where to travel to find the solution. So it's a numerical method which requires some updates, some iteration to be able to find the final solution, final destination. That's where we need that Jacobian matrix. Have you ever heard that Newton-Raphson method? Yes. Never heard it? Fine, you can take a look at the Khan's Academy. They will explain it to you. So it goes such the way that, I'm solving this nonlinear equation by using the Newton-Raphson method. Really the key component here is this delta, which is not the solution, but is a direction that allows me to update my generalized coordinates. And while, keep on updating that, I finally will get my solution. That's how it goes. I need to repeat this procedure a few times to get the solution at one time step. Then when I'm adding time, I need to do that again. Then I'm adding time, I'm doing that again, but that's how it goes. Okay, so this is a big painful mathematics. So what I'm doing here is that I'm adding that delta to my constraint equation. So I have my constraint equation, which originally was written like this. Now I'm adding that delta to my generalized coordinates, that minor ingredient, that minor adding. And this is just mathematics, so don't get too confused about mathematics. Now I'm using something that is called Taylor series to figure out the residual, the small displacement change. So this equation can be written in such the way that I have my constraint equation, and then I'm taking the partial differentiation of the constraint equation with respect to my variables, and that is then multiplied by delta on my variables. Then I have higher order terms and higher order terms, but I don't care about that. I want to neglect all these higher order terms and focus on this part. This part. So how it goes, using this part, I can find the relationship. I can actually I'm able to express how is this delta. So I'm simply taking this one here to another side of the equation, which is a right hand side of the equation, and then I'm inverting something that is called here Jacobian matrix. It's a matrix because C here is a vector, Q here is a vector. So once you do this mathematical operation, you end up to have a matrix. Look what I have to do here to get the solution. I have to take an inverse. So it has to be skew matrix. Otherwise, I cannot do it. Other limitation may follow as well, but have to be a skew matrix. What it means, I have to have equal number of constraint equation and unknowns. C and Q, they must have same number of components, otherwise this will not work out. This one here is called Jacobian matrix. Very important for us, very important. So this is partial operation of constraint equation with respect to generalized coordinates, and based on the Jacobian matrix, you can immediately tell what are the number of degrees of freedom, because look, number of rows is equal than the number of constraint equations. Number of columns is equal than generalized coordinates. So if I have a skew matrix, I have kinematically driven system, my number of degrees of freedom is 0. More stuff is coming, so now let's look. I know that you want to go home and you desperately want to go home, but we have this problem that the door is having these two joints, so we cannot escape. So I'm gonna keep you as a hostage, days here, and we're going to learn like more and more multi-body system dynamics. One more example, and then I will let you go back home. And this is this simple mechanism that we look at. This mechanism that consists of two constraint equations. How is that we can create the Jacobian matrix for this mechanism? And what will be, let me ask you this first. What would be the dimension of Jacobian matrix? How many rows and how many rows? 2, because I have two constraint equations. How many columns? 3, because I have 3 generalized coordinates. All right, so it goes this way. This is my constraint equation. I'm simply taking this constraint equation one at a time and differentiating them with respect to my generalized coordinates. My generalized coordinates are Rx, Ry, and angle theta. So I'm going to take my first constraint equation, differentiate that with respect to my first generalized coordinates, which is Rx. Okay, so let's do it. So once I differentiate that with respect to Rx, this is the only place where the Rx exists. It's going to give me 1. Then I'm going to take this very same constraint equation and differentiate that with respect to Ry. Ry is not in this equation, so it's going to give me 0. And then I'm going to take this equation one more time, this constraint equation, and this time differentiate that with respect to angle theta. Angle theta is here. So it will be non-zero component. So it will be minus L divided by 2 multiplied by sine theta. Then I redo the whole thing, except this time I'm going to take this constraint equation. I'm going to differentiate this first, the second constraint equation first with respect to first generalized coordinates. 0. With respect to second generalized coordinates, which is Ry, that's going to give me 1. And with respect to angle theta, it's going to give me minus L divided by 2 multiplied by cosine theta. What's the number of degrees of freedom? 3 columns, 2 rows. Excuse me. 1. Unbelievable. Beautiful, isn't it? I was just listening if someone is crying already this time, but not yet. Which is all right, because the crying will be coming on next Monday. Next Monday, we're going to solve the kinematics, and it's going to be very emotional moment, very emotional. So take some, some water with you, some hand, something that you can wipe your face, and come back on Monday. Okay. All right. Good. So, let me see look at what I'm going to ask you on Monday. Jacobian matrix tells you physical dimension of body, color of the body, number of degrees of freedom, how forces are imposed to body. C, but look at the color. You don't like the color. It's black all the time. Oh, no, it's white all the time. Think about it. Yeah, that sounds good to me. Sounds really good to me. All right? So let me close the recording. Let me stop the streaming. And see you on Monday. And I desperately hope that there will be no technical difficulties on Monday. That's what I hope. Reality may be different.
What is a square matrix?
What is what?